Everyone, I'm pleased to present our paper, CompSlider, Compositional Slider for Disentangled Multiple Attributes Image Generation. In this work, we address the challenge of achieving fine-grained control in text-to-image generation. In recent years, text-to-image generation has made a remarkable progress. Traditionally, users control outputs through prompt engineering, but this often lacks fine-grained control. An alternative is slider-based generation. As shown here, text specifies the main concept, while slider provide fine-grained continuous control over attributes. For example, we can adjust the dog smell or change the style of landscapes. This approach makes generation more flexibility and user-friendly. However, challenges remain ensuring the slider values reflect the smooth and continuous changes, and preserving structure consistency such as identity across adjustment. Prior slider methods train a separate model for each attribute, such as age, complexity, or style. This requires fine-tuning multiple adapters and running several forward passes during inference. But in practice, images usually involve multiple attributes at the same time, and users want to adjust them simultaneously. Existing methods ignore the disentanglement among attributes, so changing one slider often unintentionally affects others. Our idea is to design a single compositional slider model that handles all attributes together, enable disentangled multiple attributes control in just one forward. Here we illustrate the problem with prior individual sliders. When we apply the same slider value, the intensity of the smile actually changes depending on the age value. For example, if we apply the age slider before smile slider, the prior individual slider will give you an open mouth man. But if you apply smile slider before age slider, this prior model will give you a closed mouth man. So this shows that attributes are entangled rather than independently controlled. But our method can get the consistent result. We will introduce our method. We mentioned before, our method is to equip a slider to a foundation model, a T2I foundation model. So this is the pipeline of our T2I foundation model. Our pre-trained diffusion foundation model accepts the T5 text token and the image condition if users provide the source image. So it can generate images based on these two different conditions. Our high-level idea is if we can projection the slider values into an image condition just like clip class token, image class token, then this slider value, the semantic in this slider value should be recognized by our foundation model. The benefit is we don't need to access to the pre-trained diffusion model. We don't need to fine-tune it. We don't need to recall the gradient backward. I want to introduce how we train our CompSlider. Let's start from the training image. Ideally, we want the ground truth slider value from this training image, but we cannot obtain it. So we assume that the scores from pre-trained classifiers can serve as pseudo labels for slider values. The intuition is simple. The higher the classifier score, the stronger the presence of that attribute in the image, which is naturally aligned with the semantic of a slider. So with these slider values, we can send this slider value with the image caption in the form of T5 text tokens to CompSlider and generate clip image class token. The image class token was supervised by the vector from clip image encoder obtained from training image. With this simple diffusion loss, our CompSlider could project different attribute slider values into the same image space of the clip So our foundation model could be recognized and be responded to these different attribute values. The issue is that the single diffusion loss cannot make sure every attribute in the CompSlider will be disentangled. So if we have the paired data, such as the same person both young and old, or smiling and not smiling, it will be easy to disentangle this attribute, but we don't have, so we choose to random sample some values. Random sample have an advantage because if you can generate the corresponding image class token according to random sampled slider value, this means the slider value should be disentangled. This is our higher motivation. So we random sampled some slider values, but we also can input the same caption with the training image, and we can get the random edited condition, but we don't have the ground truth to separate it. So we choose to use a new inverse classifier to extract the difference between the original image class token and our random image class token. If our inverse classifier could recognize the difference, that means the generated random edited condition will be the correct. So at the same time, we also need to make sure the same caption will provides the same identity or structure. So we still have a normalization loss between the edited condition and the random edited condition. Let me now explain how we evaluate slider-based generation. Existing works mainly report LP-IPS and the clip score between images generated by foundation model and by the slider model. That metrics capture semantic correctness, but they don't fully reflect the unique requirements of slider control, such as continuity or disentanglement. So we introduce 4 new metrics based on deep-face attributes classifiers. Continuity means check whether higher slider values consistently lead to stronger classifier scores from the target attributes. This measures how precisely each slider control is attributed. The second is the scope, measures the adjustment range of a slider, computed as the difference between maximum classifier score vs minimum classifier slider score. So the third one is consistency. Verify whether image generated from the same prompt under different slider values still represent the same identity. That's testing structure stability. The last one is entanglement. Measures whether change one attribute affects others. Lower ratios indicate better disentanglement. So compared to prior text-based editing method and slider-based editing method, our method achieves the best performance. And for some slider attributes, we cannot use some open source classifier to obtain it. We choose to do A/B testing for the sliders. So compared to the SOTA slider-based method, our method achieved better preference. This page shows our evaluation study on disentanglement and structure losses. We can see that with the single diffusion loss, the consistent continuity and the entanglement is very high. When we add the disentanglement loss, the entanglement ratio dropped a lot. And continues with the consistency loss, our continuity and consistency increased a lot. Due to the normalization between random sampled slider values with the set values from classifiers, the edited scope will drop a little, but we can make sure that identity will be the same. We also provide the visualization result with these three loss. For example, with the simple diffusion loss, when you just want to increase the age, the smile unintentionally increased. But with the disentanglement loss, we can make sure the intensity of smile unchanged. We only change the age in the result. But the identity are changed a lot. So with the structure loss, we can make sure everything will be the identity will be the same, and we only control the age to increase and keep the intensity of smile unchanged. This is a comparison for human-related sliders. Both approach can successfully control the attributes of interesting. But our model demonstrates significant better continuity, control, and consistency. You can see for the age slider, concept slider will add a head, or in the first three images, it doesn't change the age intensity. So our results are showing better continuity, control, and consistency. So this is a comparison for non-human related sliders. We can control the complexity of the skin and the vector style. This is another benefit of our approach. It supports simultaneous control of all sliders with different values. Unlike prior approaches, they only allow sequential attributes control. And we also explore various combinations of different attributes. We are happy to see for some physical attributes, our slider also could work well. In this paper, we propose a CompSlider, a compositional slider model could achieve disentangled and consistent multiple attributes control in text-to-image generation. Our main contribution is to design a training strategy use random sampling, which can disentangle attributes without paired data. And we also add two different loss, the disentanglement loss and the structure loss, to make sure each slider want to infect with others. And we also can preserve the identity and the structure. So our extensive experiments and user studies demonstrating our model have better controllability and consistency. Thank you for listening.